firsthand and insightful presentations. Therefore, special thanks from TrendForce and LED Forum to our planet sponsors, Extron, Vico, Delta, GT Advanced Technologies, Tankor, KLA Tankor, Merck, Osram, Epistar, Philips Lumilus, OVAC Solutions, Taiyo Nippon Senso, and Nippon Jipan, and our silver sponsors, Lighting Japan and TESS. Our speakers today will discuss the future direction of LED industry. At this time, please take a moment to set your cell phones in silent mode. Thank you for your cooperation. 极邦科技和 LED 英赛感谢各位的莅临。这次能为大家带来这么精彩的研讨会，主要要感谢我们的白金赞助商 X 厂、台达电子、金源光电、易光电子、吉特先进、汉高、欧司朗、大洋日酸、微科仪器、多贝克科技、木科集团、美商科磊、Philips Lumilus 及云峰集团。也非常感谢我们的影集赞助商 Lighting Japan and 太一节能系统。Our keynote speaker today is George Crawford. 今天我们第一位的演讲者是目前任职于 Philips Lumilus 的皇宫发明人 George Crawford， 带来的演讲为新时代 LED 照明的应用革新。Ladies and gentlemen, please welcome George Crawford.
So my name is George Crawford from Philips Lumilus, and I'm going to talk about, as it says, LED innovations in next generation lighting. We'll outline, we're going to start with some marketing slides to talk about what's happening in the market today, and then some technology projections that we think are going to happen. And then I will talk about some of the things that are actually being done before I summarize. So this pie chart, which is Strategy Unlimited data, and this was shown in February of this year, and it shows the LED market for 2010. And it was about $11 billion in 2010. And just a couple things I want to point out, that the big parts of the pie are the mobile market and the backlight market. Lighting that we're talking about today was 8% of the market, which is actually less than $1 billion in sales in 2010. Now, one of the interesting things to me is in February, when they made this pie chart, they predicted that in 2015 the market would be $19 billion for LEDs. And then just recently they came out with a study, Strategies Unlimited came out with a study of high brightness LED, and they predicted that in 2015 the market would be $15 million, and it would peak in 14 and then be going down in 2015. So the change from 2010 to 2015 was $8 billion, and now it's $4 billion in 7 months. So what this says to me is that neither Strategy Unlimited nor I think anybody else knows what's going to happen next, really. So we're all kind of guessing what's going to happen, but there are some underlying trends, and one of them is in this big section. There has been tremendous price erosion this year, like 30 to 50%, depending on who you talk to, and this was unexpected, so that drove the price down. But underneath all of that, the other thing that's going on is the lighting market is still doing pretty well. And this just shows where on the adoption cycle the different technologies are. The backlighting market is clear over here. It's a pretty mature technology, kind of a consumer issue, and the price is coming down fast. Cell phones are, again, very high penetration level. Lighting is earlier on the cycle and coming up in market penetration. And the way the LED lighting market looks to Strategies Unlimited and to Philips, this is a combination of internal data and Strategies Unlimited, is that here in 2010 it was $1 billion, and we think that the LED market by 2015 will be over $4 billion. So it will grow by 4x or more, we think, by 2015. So the lighting part of the market is very healthy. It's just too small to overcome the price erosion from the whole big parts of the market. If you look at the actual luminaire part of the market, So this is now LED-based fixtures, luminaires, retrofit bulbs, all the things that are listed here, all these different segments of the market. It was about $3 billion in 2010, and it's going to $46 billion by 2015. So it is increasing by 15x. So those of you that are in the business of using LEDs for different applications in the lighting area, this looks like a very promising, rapidly growing, large market. So it's a great place to be. So in spite of the fact that the overall LED market is going through some strange cycles, I think there's room for tremendous growth in this part of the market. So it's a good place to be. Now this 45 or $46 billion agrees with what the Philips company projects. Yesterday, a couple people showed a slide that Philips had made a projection in 2009, showing that by 2015, half the market would be LED-based fixtures in terms of dollars. This is actually a new slide from September 2011. And so still, very recently, Philips believes that 50%, by 2015, 50% of the market will be LED-based lighting, and this is about the 45 million, so this is consistent with the previous slide. So again, we think that the market for lighting is a very positive, growing, healthy market. So what is driving LED adoption? I've tried to summarize that on this slide, which lists a lot of the things that customers care about. System efficacy is at the top, and always very important, price, reliability, total cost of ownership, global warming issues, incentives, and then down here are all these things related to the quality of the light that you get from LEDs, which has become more and more important, particularly for interior applications, to have devices that really look as good as a conventional lighting. And so you can kind of, you can boil this down to luminous efficacy and lumens per watt and lumens per dollar cost. And these two are very tightly linked, because the more lumens you get out of a single device, the more lumens per dollar you get out of a device. And also in terms of system cost, the higher your lumen per watt performance, the less heat you generate in the system, and so the lower the cost of the heat sink. So not only does the LED cost less, but the system costs less. So this is really important. And I've been in this business for well over 40 years, and always lumens per watt or brightness has been what we sell, and brightness has been the key thing, and it still is. But it's coupled with cost, which is a critical parameter, and quality of light is the other thing. And I'll talk about these three issues now. So first, the projections. This is the Department of Energy projection showing conventional lighting and showing LED and the power LEDs. This is power LEDs actually, and this is the curve that we have seen over the last decade, up to over 100 lumens per watt. And this is the prediction for the next 10 years. Now, when I say Department of Energy prediction, that's really a group of experts from companies that get together as a panel and make their best estimate as to what will happen. And this estimate of over 200 lumens per watt by 2020, I think is a reasonable estimate. We'll see. There have to be some inventions that have to happen, but clearly there's a lot of room to improve. We will clearly go from around 100 to over 150, and I think the 200 is reasonable. So we have a lot of performance gain still ahead of us. This figure, which I know you can't read, but I just wanted to use it as a talking point, or at least those anywhere in the front for you rows can't read it. This is from the multi-year program plan, which you can get on the web, the Department of Energy multi-year program plan from May, and you can, like I say, go online and look that plan up, and it talks about what this committee predicts and has all this information in it. And basically, the point I want to make is this is cool white and warm white, and today at about 100 lumens per watt, it's about $50 per kilolumen is what you pay for an LED, about $50 per kilolumen. But the projection is when you get to 2020 and get up to over 200 lumens per watt, it will be about $1 per kilolumen, or about 1,000 lumens per watt. So that's what the Department of Energy thinks is going to happen. And I think that's going to happen too. I think we're going to see that kind of price, 1,000 lumens per dollar, or even better. I actually think this is a little conservative. Okay, so now let's look at how we go about doing that. How do we get a 10x or even greater improvement in lumens per dollar? That's a big number. And the way we look at it is you have to break it into pieces. And there are two big pieces. There's performance improvement, which is lumens per millimeter squared. And there's cost reduction, which is dollars per millimeter squared. These are the two pieces. And I think roughly the breakout will be equal in those two pieces. In the performance part, there are two pieces to that. One is just lumen per watt improvement, and the other piece is current density improvement. So if at the same current through a device you get twice as many lumens, then your lumens per watt doubles, and that helps your lumens per dollar by a factor of 2. If you can drive it at higher current, you can drive it at twice as high a current or 4 times as high a current, that gives you 2 or 4 times as many lumens, so that's a huge impact on your cost per lumen. The other area down here is new technologies, which is primarily package design, and you have to have new packages that are low cost, and also have to have devices that satisfy the quality of light issues that I was talking about earlier. And finally, down here there are many manufacturing related issues, design for manufacturing, yield utilization, equipment efficiency, etc. I'll talk about that too. So I'm going to go through these different blocks and talk about the kinds of things that are being done to address these issues. So first, the efficiency issue. I've shown this slide before. I may have shown it last year or a similar one. This shows the different pieces that go into lumens per watt efficiency. There's internal quantity efficiency, electrical efficiency, which is really forward voltage, extraction efficiency, phosphor efficiency, and package efficiency. And the two areas that have the most room to grow are this internal efficiency and the phosphor efficiency. So there's a lot of effort being focused on those two areas. Now, since last time I showed this, there has been improvement. Oh, I didn't say. On this slide, the red bar is what we regard as the practical limit for these different parameters. You can't get 100% efficient in a device, but these are the practical limits, and the blue bars kind of show where a state-of-the-art device is today. So the blue bars are getting closer, but still today, internally quantity efficiency and phosphor efficiency are the areas that show the most potential for growth, and so that's where a lot of the effort is being focused. And when you look at lumens per watt, this is data, this is internal Lumileds data. Get greater than 75% lumens per watt up here, approaching 80% for all different wavelengths. We think that can go to 90. This is a 350 milliamps through a device. But this is a pretty good number. But what you want to be able to do is do this at higher current densities, maintain this kind of efficiency at higher current densities, and also increase the efficiency even higher. And the difficulty with doing that is you have to do many things at once. One thing is shown here. This is the hot-cold factor, where at room temperature, this is the performance. Many devices on the market today, when they go up to 85 degrees, drop by 10% in performance. And you use the device out here at 80 degrees, so that is basically not, your useful light has been decreased by 10% by the time you get out here. So we have worked with the epi structure not only to make it brighter, but also to maintain a good hot-cold factor. And other things you have to do are maintain low forward voltage. and you have to maintain high light output after a long time, after thousands of hours of operating conditions. So you have 4 different parameters you have to balance all at once when you're making changes in the epitaxial structure. This is a big challenge for the researchers. This is a very complex problem. You can make it brighter, but then maybe it's unreliable, or it has a high VF, or it has a bad dot fold factor. And so it's taken a lot of work to improve this. And one of the most difficult problems to deal with has been the issue of driving at high current density, where there's a very large potential cost reduction if you could drive it 2 times higher or 3 times higher in current. And these show numbers of a good device, 350 milliamps. And this shows the performance of 150 lumens per watt, 150 lumens flux coming out of 350 milliamps. In the future, what we'd like to see would be basically these same efficiencies, maybe even a little better, such that we could have a device with a luminous efficacy of 150 and 1,000 lumens of flux coming out. This would be a light bulb in a single chip, and this has kind of been a dream of mine, at least for a decade, to have such a thing, to be able to do a device like this. Unfortunately, where we are is shown here. When we go to high current densities, the efficiency is no longer 80%, it's down to below 60%. So this is the big change between these 2 curves. So this is the effect that we call droop, is this business of the efficiency falling as we go to high current densities. Now the likely mechanism, we believe, is Auger recombination. And we have thought that for quite a while. We published a paper in 2007 suggesting that. That was the first paper to suggest that. Most people didn't believe that was the case. Now, actually, most people think it is the case. There have been several theoretical papers, and there's one that I see isn't on here. There was just a couple months ago, there was a paper from the theoretical group at University of California, Santa Barbara, also saying it was Auger recombination. So there's a large group of researchers that think Auger recombination is causing this, but it's not 100%. There are also people that think it's something else. So this is still an issue in the technical sessions as to what is really causing droop. Is it Auger or is it something else? Yeah, and so the way the droop looks is the efficiency is high at low currents and then falls off. We would like it to go up and stay flat across here. If you make the recombination bigger with a double heterostructure, multiple modes, you can get this kind of structure. You can improve this a lot. But then you still have to deal with all these things I mentioned before, forward voltage reliability, all these things. So it's been difficult to fix this. I still think we will be able to fix it, but we are still working at it after quite a while. And Dr. Nakamura talked yesterday about semipolar, non-polar substrates as being a way to address this, and he thinks that will be the solution. And maybe he's right. I mean, this is an open issue as to what will finally be the solution to that. If you go with if you do have to go with semipolar substrates, then you have to develop a substrate technology that's, makes large uniform wafers, and this is a difficult challenge and will take a while. So we'll see. This is one of the interesting things that's going on that we will have to learn about over the next few years. So lower current density reduces droop. Okay. So what else is going on? To get into the next cost reduction issue is packaging device trends. Well, one of the things that's happening is larger chips are being used because since we can't solve the droop problem, larger chips give more lumens per watt. Now this goes counter to the idea of reducing cost because now you're putting in more epitaxy into a device. However, if you still put it in the same package, your package cost didn't go up, your chip cost went up a little, but you get a lot more lumens out. So in the end, you get a little better lumen per watt performance. You get a better lumen per watt performance, and you get a few more lumens per dollar by using larger chips. So this is this is definitely what's happening right now with many devices. I look at this as a transient, short-term trend. I don't know how long it'll take, but if we can solve the droop problem, then this will go away. We'll be driving it harder and making the chips smaller again, which is what we were hoping to do before. But anyhow, this is going on, and so you have a lot of the highest performance devices now use larger chips. Also, arrays of many kinds are coming into the market. A few years ago, there were just a few arrays. Now there are quite a few. And these are application specific, and they also can reduce the cost in lumens per dollar. This is a photograph of one of the LumiLED's arrays. And another issue that people have been working towards is freedom from binning. When you make LEDs and you start with the blue LED and there's a distribution and you put on a phosphor, that makes a bigger distribution. You get lots of different color bins. That costs the manufacturer money because the manufacturer has to keep track of those, and it costs the user a lot of hassle because they have to pick certain bins. And so we have had this dream of freedom from binning, and we now have products that have that. So this is a step towards ultimately reducing costs and making devices simpler to use. This slide just shows that array that I showed in the previous slide. It's a 9-chip array. It's designed for spotlight applications, and this device does have all the device. If you buy this device, if you buy a 3000 CCT device, it will all be in one bin. It will all be in a single 3-step mechanical lips bin, and furthermore, that bin will be targeted hot. It'll be measured while the device is hot to make sure that we really know what the performance is in operating conditions. So that gets us into this issue of what we call illumination grade devices, where the issues are data available for real world operating conditions of 85 degrees, these different quality of light metrics, CRI, color temperature, color over angle, and so forth, and bin sizes appropriate to the application, and publicly available LM80 reports, and product reliability data. So all these things go into having a product that we regard as an illumination grade product. And just some of the metrics that we use for color rendering, there are differences for different color temperatures, but over 80 also consider R9, test the devices at 85, 3 mechanical labs, 10 points on the E prime D prime scale for consistency in the beam. And this often people don't think about, users don't think about, is color consistency over time, not just lumens over time, but color consistency, because many devices start out with a certain color, and then after 2,000, 3,000, 5,000 hours, often it's the red phosphor will change and the device will get bluer or will change a lot in color. And this causes a lot of problems in the industry, so we have worked hard to avoid that, or to fix that. So the main thing that is worked on is phosphors. You start with the blue LED. In our case, it's a flip chip with no wire bonds, and this enables us to put on a ceramic plate, which is shown up here. So we can make the blue LED with the flip chip, we can test it, we can make the ceramic plate, we can test it, and then we can match the plates and the LEDs to end up with a tighter distribution, so we can get a single color bin. And as I mentioned, we tested at 85 degrees C, so maybe at room temperature, this is just a cartoon, but maybe at room temperature it would be like this, but when you go to operating temperature, real use temperature, all the points are very tightly within a 3-step mechanical lips. So we test here. Now, if a manufacturer, instead of testing here, tests at room temperature, puts them into a bin at room temperature, and then goes to operating temperature, this can happen, and you can get big color differences at operating temperature. So we have tried to help the users with that, and I think this is a trend in the industry to do this, to make the devices easier to use and make them suitable for illumination applications. So if you do this, then you can buy a whole bunch of devices, and you can use it in an application like this. And these are very difficult situations when you have a lot of LEDs side by side in a row. Your eye is very good at picking out differences. And so it's important to have really good control of color to be able to do this. And this is just one of our products that have this Luxion A, that Luxion S that I showed earlier had it. This is Luxion A, the one award at Light Fair that has this characteristic of freedom from dimming. Okay, the other area on that chart of reducing cost is the manufacturing issue. And there have been several talks yesterday, I think, by 3 different MOCVD manufacturers in the past, and still today in many places. The machines, aren't automated. That's changing, it's rapidly evolving, and we all heard the talks yesterday, I think, some excellent talks about the different kinds of machines, where there's cluster tools and robotic handling and subjects. So this is definitely a trend to improve the equipment. This will reduce the cost a lot. Another piece of it is the substrate issue. Sapphire substrate is the dominant substrate today, and sapphire wafers are getting bigger. And going to 6-inch sapphire is now the trend, in our lab and in many places are looking at it. So that will reduce costs going to larger areas. Other possibilities of substrates are gallium nitride on silicon, which would also enable a large area substrate. And this has been a hope for a long time. And in fact, we have a Department of Energy program working on gallium nitride on silicon. And this shows some of the numbers we have. This is milliwatts at 350 milliamps of over 400, which are pretty nice numbers. I think there are some numbers in the literature that are a little better than that at 450, but when it's in the 400s, they're good devices. So you can grow very good devices on silicon. Of course, they haven't had all the life testing and all these other testing that the devices had on sapphire, but you're getting some good results. The problem is there's so much competition in lumens per watt that the performance on the silicon wafers really has to be as good as the wafers on sapphire, or people just really won't buy it. So there's still this step where the silicon devices are good, but not as good as the devices on sapphire, and that has to be bridged. And it's difficult because silicon, there's a lot of dislocations that occur when you go on silicon, and the thermal mismatch is very large. So this is another big technical challenge. What the future substrate will be is not clear. Sapphire is a pretty good guess. It's doing pretty well, and it's hard to dislodge in entranced technology. It could be gallium nitride on silicon, or again, Nakamura yesterday talked about off-axis gallium nitride growth. Conceivably, it could be that. That would be a few years out because you have to scale it up. But at any rate, it's unclear what the substrate will be, but there is work going on in that area. Okay, this is last slide. This shows fab capacity by region in 2011, and these data were from semi-opto-ed fab forecast in March of this year. And I find this interesting that this is like 6.5 million 2-inch wafer equivalents per month. And any way I do the numbers in terms of the different applications that are out there, it seems to me that this capacity is much larger than all of the applications that I can see. It's not larger by 10%, it's larger by some factor, at least 2, maybe 3, possibly 4 times bigger. So there's just a lot of capacity already in the market, a lot more than we really need for the applications we have if the machines were being utilized as well as they could be used and run 7 days a week and around the clock and all this kind of thing. So it's almost like there's enough capacity out there in the market to satisfy not only today's market, but probably the lighting market for quite a while if the machines were really used, and still we're selling more machines. So this, to me, is another interesting thing that I don't fully understand. You could say, is the yield going to go up and the cost going to come down, and we're going to use this machine and not need more reactors, or we're going to keep selling more and more efficient reactors and displace these machines? It'll be a mix of all that, I think. I think there'll be a lot of reactors sold. There'll be a lot of them probably taken out of service, but I think there's going to be, my view is there's going to be a pretty big shakeup over the next few years sorting all this out and getting to higher efficiency, lower cost epi production. Okay, so that's gets me to the summary slide where the LED-based general illumination solutions are available and being used. Market requires higher efficacy, always higher efficacy, cost and higher quality of light, and these reductions will be achieved through a lot of the innovations by various manufacturers of the types I've talked about. And by 2020, it's predicted that the cost per lumen will be down by at least 10x, and 90% of the lighting will be LED based. So that is the end of my talk. I did want to mention one other thing quickly. Next year, yesterday, Professor Holniak was mentioned by Dr. Liu about he was the first person to make a really high performance direct band gap LED, and there's going to be a seminar in honor of the 50th year anniversary of this next October 24th and 25th at the University of Illinois. And if you're interested, then there'll be a lot of we hope a lot of eminent speakers there. So if you're interested in this seminar, Milton Feng, mfeng@illinois.edu would be the person to contact to find out about that seminar. Okay, so that's it. Thank you very much.